Okay, so today we're going to look at the convergence tests that were cut out of the AP curriculum. They are the comparison test, which we have here, the limit comparison test, and the root test. So the comparison test and the limit comparison test work like this. We have to pick a series that we already know either converges or diverges. And then we have to prove that that series is related to the given one in a certain way. And then once we do that, the given series will act exactly the same as the other series. So here's the way this works. For the comparison test, we'll consider two different series where every single term in those series is positive. So not alternating series. Basically, this could work because we know what absolute convergence is. If we took the absolute value of each term, we could check if one term converges absolutely, and then that would show the other series converges absolutely. But we're dealing with just series with non-negative terms. And we want one of the terms of the series, one of the terms of our series, to be less than or equal to the equivalent position of the terms of the other series. So we would want the 0th term in the first series to be less than or equal to the 0th term in the second series. The first term to be less than the first term. The second term to be less than the second term, and so on, for every single value of n. When we talk about this, again, we can get into the eventual, where this eventually happens. Then, if the larger series converges, the smaller series converges. And that should make sense. What I like to do with that is I like to think of this as being almost like an explosion and an implosion. So if this is my smaller series, A sub n, and this is my bigger series, B sub n, and we talk about convergence, let's pretend that B sub n is going to converge to this point. So like this circle is going to contract. So B sub n is the bigger series. That's why it's the bigger circle. If this circle is going to move inward, and go to this point. Since A sub n is smaller, notice that as B sub n contracts, it's going to kind of take eventually A sub n with it and push A sub n down to this point as well. So if we have two series and one of them is larger than the other, and the larger one converges, the smaller one has to converge. Likewise, if the smaller series diverges, so now pretend that this A sub n is diverging. So instead of going to the point, it's getting larger and larger and kind of just exploding. Well, what's going to happen is eventually the A sub n is going to get to the B sub n and push it out. So if the smaller series is divergent, then the larger series also diverges. So that's the idea. We have two series. One of them is always larger than the other one. If that larger series converges, then the smaller one will converge. If the smaller series diverges, then the larger series diverges. If the larger series diverges, if this shoots off and explodes, we don't know anything about the smaller one. And if the smaller one converges, we don't know anything about the larger one. So here's the way this works. We're given this series, 1 over 3 to the n plus n. And we need to figure out if this converges or diverges. And we need to choose a series to compare it to. So what we tend to do is we tend to pick series that we have a way of testing to know very easily if they converge or diverge. Namely, we tend to pick either geometric series or p-series. So for this one, since I notice this has a 3 to the n, and as n gets really large, the 3 to the n is going to take over, I will compare this series, choose, to n equals 0 to infinity, 1 over 3 to the n. So that's what I'm going to do. And the reason I choose this is a geometric series, and I know something about this. This series is a geometric series, and it converges because r equals 1/3. And 1/3 is in between -1 and 1. So I know the series I've chose converges. So I'm going to be looking at the first piece of the comparison test. So I picked a series that converges. Now all I have to do is show that my series is larger than the given one. So to show, I need to show that every single term in the series I chose is greater than or equal to every term in the series that was given to me. And this is easy enough to show using basic properties of inequalities. So let's start with this. We know, so here's what we're going to do. We're going to prove it. Ready? We know that 3 to the n will always be less than or equal 3 to the n plus n as long as n is a natural number or 0. And again, those are the only ones I'm concerned with because my summation starts at 0. Well, when we have an inequality, if we take the reciprocal of both sides, what it does is it changes the direction of the inequality. And right there, that's what I wanted to show. Therefore, by the comparison test, the series that we were given converges. Now, sometimes when we do this comparison, we have to do it a little differently because we don't have as nice an expression. So here's another one. This one, when I look at this given series to me, I notice that this is a rational expression here. N squared minus 2 is polynomial, n to the fourth plus 5 is polynomial. This was not a rational expression because it had an exponent in it, an exponential function in it. So since this is a rational expression, as n goes off to infinity, this is going to act a lot like n squared over n to the fourth. The 2 and the 5 will become negligible. And n squared over n to the fourth is the same thing as 1 over n squared. So I'm going to choose the series 1 over n squared. And we know that this series converges, because it is a p-series with p equal 2. And since that's greater than 1, I know that this series converges. So now, the only thing I have to do, since I picked a series that converges, is I need to show that 1 over n squared will always be greater than or equal to n squared minus 2 over n to the fourth plus 5. So this is going to be tricky. It's not as easy because notice here I had just 1 over each piece. So it's easy to flip them. Here I don't necessarily have that. So this is going to be a little trickier. So what we can do, if I want to show this, I also realize that's the same thing if I subtract this expression from both sides, of showing that whenever I subtract these things, it's going to be positive. And now I can get a common denominator, n to the fourth minus 5 over, and if I multiply this by n squared, I would get n to the fourth minus 2n squared all over n squared, n to the fourth plus 5. I need to show that this is greater than or equal to 0. And if I do this, I get that 5 plus 2n squared over n to the sixth plus 5n squared needs to be greater than or equal to 0. And we're done. I just need to now go back this way. I need to show this, which is the same as this, which is the same as this, which is the same as this. 5 is always positive. 2n squared will always be greater than or equal to 0. N to the 6 will always be greater than or equal to 0. And 5n squared will always be greater than or equal to 0. Therefore, this will always be greater than or equal to 0. Which means this term will always be greater than or equal to 0. Which means this term will always be greater than or equal to 0. Which means this expression will be true. So I did it. Therefore, by the comparison test, the series I was given, n equals 1 of n squared minus 2 over n to the fourth plus 5, converges. And again, you might notice, this is tricky. Choosing which series to compare to can be tricky. Especially, what would happen if I picked 1 over n squared, I knew it converged, and then it turned out I couldn't prove this? Well, I'd have to go back and pick another series. Maybe I would pick something that diverged and show that this is greater than that, the divergent series. So the comparison test is very tricky to do because you have to choose a series that works. And you do enough of these problems in the same way with U substitutions, you kind of get a feel for them. So here's another example. This one involves the absolute value of sine n over n squared. So what I'm going to do, because I remember something about sine, the sine function has a range between -1 and 1. And I know that if I take the absolute value, that this is always going to be less than or equal to 1. So I will choose the series n equals 1 to infinity of 1 over n squared. And why did I do that? Because this term, absolute value of sine n, is always less than or equal to 1. Sine is always between -1 and 1. If I take the absolute value, it'll always be between 0 and 1, namely less than or equal to 1. So now, once again, all I have to do is I have to show that, well, this is 1 over n squared, and this converges by the p-series test. So once again, I just need to show that 1 over n squared will always be greater than or equal to absolute sine n over n squared. And this one is easy enough to do. We know, and here's a little proof, that 1 is always greater than or equal to the absolute value of the sine function. And then if I divide both sides by n squared, since n squared is always positive, it doesn't change the direction. I've now proven it. Therefore, by the comparison test, my series converges. Now, in all three of these examples, I picked a series that was larger, just so happened to be larger, and it converged. But there are instances where you would have to pick a series and it turns out it's smaller than the one we want, and then we show that it diverges by showing that it's smaller. So the concept works the same way. And that is the comparison test. So the limit comparison test is a very similar test. Note that here there's no actual comparison with the less than or greater than though. Instead, what the limit comparison test has us do is it has us pick a series that we already know converges or diverges. And then we take the limit of the ratio of the chosen series and the given series. If that ratio is greater than 0, then whatever my chosen series does, then so too will the given series. And the way we choose the series is pretty much the same way. So I look at what happens as n gets really large, and then I pick a series that models that end behavior to compare it to. So once again, this was the same series we had before, so I'm going to choose the series 1 over 3n as n goes from 0 to infinity, which converges by the geometric series test. And I could write down, because r is 1/3, yada, yada, yada. We did that before, but I'm going to choose this. So now what we do is we take the limit, and we examine the limit as n approaches infinity of the given series over the chosen series, or the chosen series over the given series. It doesn't matter. So this is going to be 1 over 3 to the n plus n over 1 over 3n, which is the same thing as times 3 to the n over 1. And note, since all the terms are positive, I don't have to take any absolute values or anything. This is not the ratio test. I'm not taking the terms in the series itself. I'm choosing a separate series and comparing the terms of the separate series to the original series. So what is this limit? Well, this is the same thing as the limit as n approaches infinity of 3 to the n over 3 to the n plus n. And if you remember how to deal with this, we can compare every single term by the term that's increasing the fastest, which is 3 to the n. So this is the limit as n approaches infinity of 1 over 1 plus n over 3 to the n. As n gets infinitely large, this goes to 0, and we get 1. And 1 is greater than 0. So since I got a number that is greater than 0, whatever my chosen series did, this will do. So by the limit comparison test, the given series converges. And it converges because this series I chose converges. Same idea here. What series am I going to choose? Well, I'm going to choose the series whose end behavior models the end behavior of this series. So in the numerator, this is a polynomial, and I noticed that the numerator is a 4n squared, so I am going to choose n squared. And the denominator, I have the cube root of n to the 7th, so I will choose n to the 7/3 for my denominator. And this goes as n goes from 2 to infinity, so this is what I'm going to choose. And this is equal to n equals 2 to infinity. 2 minus 7/3 is, this is 6/3 minus 7/3, n to the negative 1/3, or 1 over n to the 3rd. And this diverges by the p-series test, because p is less than 1. So now what I'm going to do, I picked my series, is I now compare the series I've chosen to the series that's given. So I take the limit as n approaches infinity of 4n squared plus n over the cube root of n to the 7th plus n squared times, this would be the cube root of n over 1. And now I can, as n goes to infinity, examine this. This would be the limit as n goes to infinity of, so let's see, this would be 4n squared plus n times the cube root of n over n to the 7th plus n squared. I could write it that way, and that doesn't really help. Let's instead write it, let's multiply this and add the exponents. This is n to the 3rd, this is n squared, so that's 4n to the 7/3 plus n to the 4/3 all over the cube root of n to the 7th plus n squared. And now this is the same thing. The largest term is n to the 7th cube root. That's n to the 7/3. So I'll multiply this by 1 over n to the 7/3, 1 over n to the 7/3. And we get the limit as n approaches infinity of 4 plus 4/3 minus 7/3 is negative 3/3. That would be 1 over n over. If I bring, this is the same thing as n to the 7th cube root. So that would be the cube root of 1. And then this would be n squared over n to the 7th. That's n to the 5th. And this is all just algebra. And so now as n goes to infinity, 2 over 7 is negative 5th. This would be 1 over, n to the 5th. And now as n goes to infinity, this goes to 0, this goes to 0. The whole thing goes to 4, which is greater than 0. So by the limit comparison test, since my limit of the ratio of these terms is greater than 0, it exists, and the chosen series diverges, the series that I was given diverges. And again, the limit comparison test can also be tricky because, again, you have to choose which series you're going to pick to compare it to. And the way to choose them, for the most part, works like this. Note that for these two tests, you must choose a series that you can use to compare to the given series. So how do you choose the series? Well, if your a sub n is a rational function or contains only polynomials and roots, meaning it's algebraic, you should choose a p series created by the highest power of the numerator and denominator. In essence, we look at the end behavior, see what our current series acts like in the end, and then we just choose the p series that models that. If it involves an exponential function, however, exponential functions increase much quicker than rational functions and polynomials. So then we would choose a geometric series that has the same end behavior as the exponential functions. You should be aware that these tests could require some trial and error since you have to choose the series to which you're comparing the given one. So you might choose a series and then it might not work. You might choose a series for the limit comparison test and get that the limit is infinity or the limit is 0. You have to choose another series. Or you might choose a larger series for the regular comparison test and find the larger series diverges. That doesn't help. Or you choose a smaller series for the comparison test and it converges. That doesn't help. You have to go back and choose another one. If you choose the wrong series, the test can fail. Like I said, then you have to go back and choose another one. For example, if you use the comparison test, and this is what I just said, basically. So I think this is why they took it out of the curriculum. These tests are rarely used. Because we have other tests that are nicer. They do come in handy on some occasions, but for the most part, anything that was done in the curriculum could be done with a different test. The final test is the root test. The root test is very similar to the ratio test in that we're taking a limit of terms of our given series, and then we determine whether the series converges or diverges based on that limit. With the ratio test, we took a ratio of terms. With the root test, we are taking a root of the terms. So let this be a series, and let L be the limit as n approaches infinity of the nth root of the absolute value of the a sub n. So once again, we're going to look for absolute convergence. If L is less than 1, the series is absolutely convergent, so it converges. If L is greater than 1, the series is divergent. If L equals 1, we don't know what's going on. The test fails. We would use this test in a situation where we have all the terms raised to the nth power. And if they're all constants raised to the nth power, I could just use a geometric series test, which I'll show in a minute. But for example, problem 1, n to the n is always a problem. N to the n is a problem because if we try the ratio test, it gets very messy. If we try other tests, it gets very messy. So instead, here's what we do. We examine the limit as n approaches infinity of the nth root of the absolute value of n to the n over 3 to the 1 plus 2n. This is the same thing as the limit as n approaches infinity of, well, since these are all positive, this is the nth root of n to the n over 3 times, this is going to be 3 squared to the 9th, 3 squared to the n, so 9 to the nth power. Okay, that's the limit as n approaches infinity of. Well, I can take the nth root of 3. That really isn't going to, be all that important. So let's do this. The nth root of n to the n is just n. The nth root of 3 is the nth root of 3. And the nth root of 9 is just 9. And this is the same thing as the limit as n approaches infinity of n over 3 to the 1 over n times 9. So as n goes to infinity, 1 over n goes to 0, 3 to the 0 is 1, the denominator goes to 9, the numerator goes to infinity, which is greater than 1. Therefore, by the root test, this series converges. Example 2, we have an entire expression raised to the nth power. This is screaming at us to use the root test. So this is the nth root of the absolute value of 5n minus 3n cubed over 7n cubed plus 2, all to the nth power. I can get rid of the absolute values and then take because this is always going to be positive when n gets large enough. And then I can take the nth root of this, and that's just the limit as n approaches infinity of 5n minus 3n cubed over 7n cubed plus 2. And we know from our end behavior discussion at the very beginning of the year with limits or L'Hopital's rule, or however you want to do this, that this is equal to 3/7. Negative 3/7. Oops, absolute value. Absolute value, which would be 3/7 as n gets really, really large. And that means that this is greater than 1. Less than 1. Whoa. 3/7 is less than 1. Therefore, this series diverges. See, I'm taking the nth root of the absolute value. I can move the n outside. The absolute value of a to the x is equal to the absolute value of a to the x. That's one of the identities of absolute value. So this diverges because 3/7 is less than 1. Last example. We could use the alternating series test here. If we try the alternating series test, we could rewrite this as negative 1 to the n times 12 to the n over n. These terms do get smaller and smaller, and they do decrease. So this does converge. So let's see if the root test tells us the same thing. So this would be the nth root of the absolute value of negative 12 to the n over n. That's the limit as n approaches infinity of, the absolute value of negative 12 would be 12, and the nth root of 12 to the n would just be that 12. And then this would be the nth root of n. And this is interesting. What is the limit as n goes to infinity of the nth root of n? In other words, here's a little aside. What is the limit as n goes to infinity of the nth root of n? If we were using the root test or even the ratio test, this comes up a lot, and so we need to know how to do it. We can rewrite this as n to the 1 over n. Well, the numerator goes to 0, the exponent goes to 0, the base goes to infinity, and infinity to the 0 is an indeterminate form. If you remember how to handle this, this is the limit as n goes to infinity of e to the ln, n to the 1 over n. I can move the 1 over n out because of the log laws, and I can pull the limit in because this is continuous. N approaches infinity of 1 over n, ln of n. This is ln of n over n. This is e limit as n approaches infinity of ln of n over n. And now both numerator and denominator of this limit are going to infinity, so I can L'Hopital it. This is e to the limit as n approaches infinity. The numerator becomes 1 over n, the denominator becomes 1 rather. And as n goes to infinity, this goes to 0. So this is 1. And that's important, because now when I take this limit, the denominator goes to 1, the numerator goes to 12. That's bigger than 1, so we converge, which the alternating series test also tells us. And that, ladies and gentlemen, is a very quick run through of the 3 convergence tests that we did not do. The only thing that's left for us to do now, as far as the original curriculum, is Taylor series and Maclaurin series. And since we already did the polynomials, the series are actually pretty straightforward. We're going to be using them power series, whether power series converge, radius interval convergence, Taylor and Maclaurin series, and the Lagrange remainder, and then differentiating and integrating. And we can get all of that done over the next week, this Wednesday and this Friday. And then we'll be good. So, yeah, that's it. And because this was a comparison test kind of thing, let's give this the Cetron comparison test seals of approval, where the small comparison test seal of approval will be compared to the larger comparison test seal of approval. If this series converged, if this series converged, then this series would converge because it's smaller. And if this series diverged, then this series would diverge because it's larger. And I'm all out of seal puns. Thanks for watching.